All right, hello everyone and welcome back. In this video, we're going to look at vertical circles. So we just got done talking about horizontal circles, and one of our examples was tying a stopper on a string and spinning it over our head in a horizontal circle. And when we did that, the speed of the stopper was constant. So we're going to do something kind of similar. So we're going to take the stopper, we're going to tie it to a string, but this time we're going to spin it in a vertical circle. So kind of like in the Y direction where the stopper's at the top, then the stopper's going to go down, the stopper's going to go up. So we're spinning in a vertical circle. And one of the key differences is in a vertical circle, the speed of the stopper is not constant. Gravity's going to speed it up on the way down. Gravity's going to slow it down on the way up. So speed up, slow down. And we find out that the speed is going to be the greatest at the bottom. And it is going to be the slowest when it is at the top. So the velocity of the object is constantly changing in this vertical path. And for that reason, the tension in the string is also going to be changing. So we are going to look at the stopper, analyze the stopper when it is at three key locations. So one of those locations would be when it's at the top, perfectly at the side, like over here, or could be over here, and when the stopper is at the bottom. And if we draw a free body diagram for each of these locations, we should be able to reason out a working equation or a mathematical relationship that we can use to analyze the tension in the string at that particular spot. So let's actually start with spot 2. So if the stopper was at spot 2, then my string would be going towards the center of the circle, and that would be tension. And my stopper still has weight, so that's FW. I'm kind of guessing how long to draw that arrow because I don't know. But I do see a stopper going in a vertical circle. So I'm going to write down the centripetal force equation, mv squared over r. And we know that we always have to replace the centripetal force with the force that is actually going towards the center. And in this case, that would be the tension. And so this becomes a working relationship that we can use to find the tension in the string when the stopper is at that spot. But now let's have the stopper go around and be up at spot 1. When the stopper's at spot 1, I'm going to draw the free body diagram. I'm still going to have tension pointing towards the center of the circle. But in this case, FW is also pointing towards the center of the circle. And again, I don't really know how long FW is, but regardless, I see a stopper going in a vertical circle. So I'm going to put down my circular motion equation, and I'm going to replace the FC with the forces that are pointing towards the center of the circle. So in this case, it's going to be tension plus FW, but I'm going to write FW as mg equals mv squared over r. I do want to point out that you cannot cancel those m's. Algebraically, you can't do that, but that's a common mistake that people do. You would be able to cancel the m's if there was an m connected to the ft and there was an m in every term, but we cannot do that. So this becomes the working relationship that we could use to find the tension in the string when the stopper is at the top. So now let's take the stopper and move it all the way down to the bottom, move it down to the bottom, and we're still going to have the tension pointing towards the center of the circle, but FW now is pointing down. But let's talk about FW for a minute, the length of FW. So in order for something to be in a circle, you have to have a net force towards the center. So that means that the long arrow always has to be going towards the center. So let's pretend the tension was 20 and the weight was 5. Then the net force would be 15 towards the center. So the tension arrow has to be longer than the FW arrow. I have to have a net force towards the center. So I was able to reason that out. And so now when I write my working relationship, I'm going to replace FC not with just the force that's going towards the center, but the net force that is going towards the center. So it's going to be the big arrow minus little arrow. And so that's going to end up being FT minus mg equals mv squared over r. So again, I don't have these memorized. I just draw the free body diagram and figure out what my working relationship is going to be. All right, but there's one more thing that I want to talk about here. So let's say I'm spinning my stopper in a vertical circle, and there has to be a minimum speed that I have to spin the stopper. And if I start to spin too slow, then my stopper is going to like fall and collapse and fall towards the center, and then I won't have a vertical circle anymore. So the question is, how do you figure out what minimum velocity is needed to maintain that vertical circle? So the disaster is going to happen when the stopper is at the top, That's where the circle would fall apart. So I'm going to look at the relationship for when the stopper is at the top, and I'm just going to copy that relationship down here. And I'm going to call this velocity the minimum velocity. So I'm going to write the word min. I'm trying to find out what that minimum velocity would have to be. So if I spin too slow, and I'm going to write that down. If velocity is too slow, then my tension is going to go to 0. My tension is going to be 0, and it's going to like fall into the center. So if the velocity is too slow, then Ft would become 0. And because I wrote that sentence, if the velocity is too slow, the tension becomes 0. Now I'm going to make the tension 0. And then I would have, I'm trying to figure out where to write this. I'm going to write it up here at the top, I think. Let me go up here. So I'm going to make the tension 0 then. So mg equals mv squared. I'm going to put min over r. Now I can cancel those m's. I'm going to divide both or multiply both sides by r. That would give me gr equals v min squared. So I'll just square root this. And the minimum velocity that I need to maintain a vertical circle turns out to be the square root of g times r, or 9.8 times the radius of the circle that I'm trying to make. And I was able to develop this relationship from this working relationship, but I can't just cross off tension without some rationale for why I'm crossing off the tension. So this sentence is important. If the velocity is too slow, then the tension would become 0, and then this would become the minimum velocity that I'm looking for. So that's just kind of a little tip trick of how you can find the minimum velocity from that working relationship. All right, now let's shake it up a little bit by going down with another example. And in this example, we're going to look at a roller coaster. And in a roller coaster, we're not going to be talking about tension. We're going to be talking about the normal force that's present on the seat as you sit in your roller coaster seat. And we are going to look at 3 key spots again. And the key spots are going to be at the top of the first hill. So the roller coaster is going to come down at spot 2. And then it's going to go up and do a loop-de-loop. So it'll be upside down here at spot 3. And we're going to look at the roller coaster when it's at these 3 key spots. So let's start with the first one when the roller coaster is at the top. And let's draw the free body diagram. So there has to be a force towards the center. That's going to turn out to be the weight of the roller coaster. But let's talk about the normal force. So the roller coaster pushes on the track, and then the track pushes back on the coaster. So the normal force is going to point up. But there has to be a net force towards the center. That means there has to be a longer arrow towards the center. So I'm going to draw my Fn shorter. And that's going to help me write my relationship over here. When I write the centripetal force equation, I see a roller coaster that's going over the top of the first hill, and going over the top of the first hill is like a partial circle there. And I'm going to replace the centripetal force with the net force towards the center. And in this case, it's going to be Fw minus Fn, or big arrow minus the little arrow. I should have wrote that as mg, just to be consistent. All right, that works for there. All right, now let's look at the roller coaster when it comes down the first hill, and now it's at the bottom of the loop-de-loop. It hasn't gone into the loop-de-loop yet. But again, this is part of a circle. And so I'm going to draw my free body diagram. There has to be a force towards the center. So that looks like Fn, the track pushing up on the coaster. Let's call it Fn. And Fw has to point down, but the net force has to be towards the center, or the longer arrow has to be towards the center. So I'm going to make sure that I draw this as a shorter arrow. And so again, this is a partial circle. So mv squared over r. And what would you put in for the centripetal force looking at this picture? I hope you can reason out that it would be Fn minus Fw, I'll write that as mg, equals mv squared over r. And now we have the coaster going up and doing the loop-de-loop. And so there has to be a force towards the center. Clearly, the coaster has weight, so I'm going to call that Fw. Let's talk about Fn. Fn is the track pushing back on the coaster. Well, because it's upside down, Fn is also pushing down. And I don't really know in this case what's bigger, Fw or Fn. So I just kind of drew them arbitrary. And again, it's a partial circle. And I'm going to replace the centripetal force with the net force going towards the center, which is going to be Fn plus mg equals mv squared over r. Another working relationship. All right, but just like we did up here, there has to be a minimum velocity of my coaster in order to be able to make that loop-de-loop. If my roller coaster came down and was going too slow, then he would not be able to traverse this circle. So what minimum velocity does he need to traverse this circle? Let's do the same kind of thing that we did above. So the disaster would happen at spot 3. That's where everything would fall apart. So I'm going to take this relationship at spot 3, and I'm going to write it up here. Plus mg equals mv squared over r. And if my roller coaster velocity was too slow, then the roller coaster would fall off the track. And if it fell off the track, Fn would become 0. So I'm going to make Fn 0. I'm going to make it fall off the track because that will tell me the velocity at which that happens. So this relationship then would become the minimum velocity that I'm looking for. The m's are going to cancel. I'm going to multiply both sides by r. So I'm going to get gr equals V min squared. And then I'll square root both sides. And I end up with the same relationship that I did up here. This was the minimum velocity for the stopper to traverse the vertical circle. And this becomes the minimum velocity needed for the roller coaster to traverse that vertical loop. So you now can draw a free body diagram of any picture or problem that you are given. You should be able to start with the centripetal force equation and then derive an appropriate mathematical relationship that you can use to solve any of the given variables or questions that you are asked. All right, I hope this helps, and we'll be in touch.